Hello everyone, my name is Behnam Pourghassemi and I'm presenting our paper titled On the Limits of Parallelizing Convolutional Neural Networks on GPUs. This is a joint work with the University of California, Irvine and Samsung. In this brief announcement, we identify the challenges and limitations and potential solutions for intra-operation parallelism of CNNs on a single GPU. With the advances of deep learning in artificial intelligence and machine learning, convolutional neural networks have shown outstanding results in a variety of fields like computer vision, image classifications, voice recognition and natural language processing, or even in physics simulations like computational fluid dynamics. Here is the structure of a simple convolutional neural network consists input and output layer and multiple hidden or intermediate layers, such as convolution layers that is extract features. Each layer consists set of weights and biases that they are learned during training process. So the whole process is time consuming. For this reason, ML practitioners use specific deep learning frameworks to implement their networks. These frameworks takes the network and compile it to basic operations such as convolution or Maxwell, and then run it on the hardware. It could be CPU or any accelerators. Majority of these learning frameworks have GPU backends that they use third-party libraries such as highly optimized NVIDIA cuDNN and cuBLAST library for the performance purposes. Here are some of the observations by running popular CNNs on these frameworks. First, convolution is the key operations in CNNs and it takes majority of training time. Second, these operations are executed serially on GPU backend. This is probably related to linear structure of earlier CNNs, where operations sequentially depend on each other, and they inherently do not expose parallelism. However, more recent networks such as ResNet and GoogleNet have nonlinear architectures that contain multiple execution paths, so it is possible to run independent operations in parallel for these networks. Third, this framework sticks to a default algorithm or the fastest algorithm. For example, for forward convolution, TensorFlow tests all the algorithms such as FFT, Vinograd, and so on in the first iterations and pick the fastest one and use for the rest of the iterations. However, the fastest algorithm is not necessarily the best because it might use a lot of resources and prevent other kernels to run in parallel. Also, third-party libraries used in these frameworks prevent multiple kernel execution. For example, our sandbox benchmarking of cuDNN has shown it is not possible to run two or multiple convolutions simultaneously with these APIs. But why cuDNN convolutions cannot be run in parallel? The reason is that there is resource contentions, primarily in device memory and compute resources, also referred as SMs on GPU. For example, convolutions use device memory to store input-output data, filter, and workspace memory, which is a scratch memory to store intermediate data, and also SM resources. But what we observe is that each convolution in cuDNN occupies all available SMs and prevent other kernels to run simultaneously. This is happening while some of the resources like registers or shared memory are underutilized by that kernel. But to reduce the resource contentions and improve parallelism in CNNs, we propose SM partitioning plus profile-based algorithm selection. There are two ways for SM partitioning. One is inter-SM partitioning that partition whole SM units among kernels, and the other is intra-SM partitioning that let blocks from different kernels to share one SM. Recent studies have shown benefits from concurrent kernel execution using SM partitioning compared to sequential execution when the static resources are underutilized or the kernels have complementary behavior. Also, careful algorithm selection can affect workspace memory, which can reduce the device memory contention, and it can affect SM resource utilization that can enhance the benefit of SM partitioning. We will show this by example later. To locate opportunities for our proposed solutions, we extensively analyze popular CNNs like Google and ResNet. We run our convolutions on K40 GPU and use NVIDIA profilers to report resource utilization, execution time, and memory usage of each convolution. We then find the cases where algorithm selections and concurrent kernel execution show benefit. Here is an example case show two independent convolutions from first inception module in GoogleNet. TensorFlow picks pre-comp-gem algorithm for both convolutions, which is bottlenecked by registers by underutilized shared memory. Now, if we pick FFT tiling for the second convolution, we will have complementary static resource utilization. Also, these two algorithms show complementary behavior, as pre-comp-gem algorithm is more compute bound and FFT tiling is more memory bound. With this algorithm selection, we could hide memory styles of the second convolution by switching to the compute warps of first convolution if we apply SM partitioning. In another example, we show workspace memory and execution time of a 5x5 convolution in third inception module of GoogleNet. Here, TensorFlow pick FFT algorithm because it's the fastest algorithm. However, if we choose vinograd non-fuse algorithm, we increase the execution time by just only 20%, but we'll save more than 70% of memory that can be used by another concurrent convolution. Overall, we've seen about 27 cases like this in our profiling that show the benefit of algorithm selection and concurrent kernel execution. However, deploying our concurrency models is very challenging because it requires exhaustive space exploration due to trade-off between execution time and workspace memory and picking the optimal operations from the ready queue. But most importantly, NVIDIA SM scheduler and cuDNN library are closed source, so we could not modify that. So in our future direction, we are trying to either to simulate our model using the GPU simulators or rewrite our own kernel on the open source library, such as the equivalent for AMD GPUs. Thank you for your attention.